For the next problem, we want to find the rate of change in elevation of the camera shown. And this is on page 184. We're filming a rocket after liftoff. So this point up here is the rocket and the camera is over here. So in the diagram, and you can look at your book to verify this, we have this angle theta here. S is the height of the rocket and the camera is positioned 2,000 feet away. Now there's this really important equation in the small print of the picture in the book that S equals 50t squared. That's an expression for how fast the rocket is rising. Okay, so S, remember, is the height of the rocket, so it's 50t squared, so that's time. So that's going to be super important as we get into this problem. So we're given very little outside of that diagram. We are supposed to find the rate of change in the angle of elevation of the camera at 10 seconds after liftoff. So really all we're given in that paragraph or that sentence is that t equals 10. We are supposed to find the change in elevation, the rate of change in elevation of the camera. So we're supposed to find d theta dt. And we do have all the information we need to do this. It just takes a little bit of doing to get there. So the equation that we want to work with, we want to relate all of these pieces. So hopefully you can see this is obviously a right triangle, and there's a tangent relationship. We can see that the tangent of theta is S over 2,000. So that's what we're going to take the derivative of with respect to time. The derivative of tangent is secant squared times d theta dt. And S over 2,000, remember that's just 1 over 2,000 S. So the derivative is going to be 1 over 2,000 times ds dt. And since we're trying to solve for d theta dt, I'm going to go ahead and do that. So I'm going to divide both sides by secant squared. So that's going to go on the bottom here. ds dt. So we get d theta dt is, now this is secant squared, 1 over secant squared. 1 over secant squared is the same thing as cosine squared. So I'm going to go ahead and rewrite it that way. So we have cosine squared theta over 2,000 times ds dt. So now we're ready to plug things in. So in order to plug in, we need to know theta and we need to know ds dt. Neither of those things were given to us. So let's see. Remember this little equation that I said was going to be important. We can find out what S is. That might be helpful. Okay, so 10 seconds after liftoff, S is going to be, plug in 10 there. S is going to be 5,000. So now that we know that S is 5,000, we can find out what theta is because the tangent of theta is opposite over adjacent. So we're just going to do inverse tangent, pop that into our calculator, and we get 1.19 radians. I'm in radian mode here. Okay, so we can start plugging in. Let me do that over here. So remember, we're trying to find d theta dt. We now know that we're trying to do cosine theta is 1.19. We're going to take that and square it, divided by 2,000. Now, we still need ds dt. So ds dt, we're going to come back to this little equation that they gave us in the small print, and we're going to take the derivative of that. Because remember, we're trying to find ds dt, so let's go ahead and take the derivative with respect to time. ds dt is, if we take the derivative of 50t squared, that gives us 100t. And we want to evaluate that. Remember, we were given that t is 10, so we're just going to plug in 10. So ds dt is 1,000. So we'll come back over here and multiply this by 1,000. And now all we have to do is plug that into our calculator. So you're going to do cosine of 1.19, remember you're in radian mode, square that number, divide by 2,000, multiply by 1,000, and we get 0.069. This is how fast the angle's changing, so our units are going to be radians per second.